Yeah, okay. All right. Good afternoon, everyone. Thank you, Caroline, for the introduction. So yeah, I'll just jump right in. We've been in charge at Radboud University as a MEDUWA partner in charge of conducting the risk assessment. And the quantification of risk, I see it as kind of setting a meeting. So to set up a meeting like this one, you need two essential pieces of information. So you need to know where, you need to know when. Without one of them, you cannot have a meeting whatsoever. So, and that kind of makes me think that it's not that different from calculating a risk, because risk can also relies on two essential pieces of information. So you need to know the exposure concentration, so the concentration at which a certain organism is exposed to, and you need to know which concentration is safe or is deemed as safe. And with that you can get the risk. And so far Volker and Gunnar have focused on the concentrations, which are essential, again, as I said, a very essential piece of the puzzle. But high exposure does not immediately imply that there's a concerning risk. We've conducted, well, we went through three endeavors. We've conducted essentially three assessments: one for ecological risk, another one for human health, and another one a little bit more experimental, but in regards to antimicrobial resistance. Yep, here you are. And as has been already presented, we've worked as well with the same selection of pharmaceuticals based on a diverse set of criteria. And on the last column on the table, you can see which ones I'll be talking about, or I'll show some results depending on which assessment I'll be talking about. So I'll start with the ecological risk assessment. So basically, we try to answer, let's say, two simple questions. Do these pharmaceuticals pose a concerning risk for aquatic organisms, and what is the spatial distribution of these risks? As a first step, let me just turn this on, the laser pointer. So here in the corner, just to remind you how we calculate the risks. So in the first step, we had to come up with the safe limits for each pharmaceutical. And for that, we've collected about 11,000 toxicological data points from different databases, reports, and from the literature that we've collected ourselves. And out of all of those data points, all that information, only 80 of them were deemed usable for our purposes. And out of those 80, we've came up with one safe limit per pharmaceutical. In this case, we looked at 8 of them. Also, as a means of comparison, we took safe limits, in this case, PNX, safe limits from the literature, and so that we can compare ours with the ones that other people have calculated. And and we've merged them in this figure. And as you can see, the red squares are the ones that we've derived. 3 for cyclophosphamide, carbamazepine, and diclofenac. They were lower than any PNEC that we found in the literature. So which could kind of change a little bit the way we see the risks in regards to these pharmaceuticals in particular. And on the opposite end, you see that for ciprofloxacin and metoprolol, for example, ours were higher than any other PNEC found in the literature, other safe limit concentration found in the literature. So now we have the safe limit, we need the exposure concentrations. And for that, we merged forces. We joined forces with Osnabrück and with the University of Osnabrück and Vechte, because they've, as you've seen, they've used the greater model to come up with predicted environmental concentrations for the pharmaceuticals. And we've used those to merge with the safe limits that we've derived. And we came up with, this is just one figure for one of the scenarios, the dry summer scenario. I don't have time to show, not in the least, the amount of information that we have. So just for the dry summer scenario. And here you see the quantified risks, and each curve corresponds to one pharmaceutical. And this relates to the amount of water volume in the entire catchment that seems, for which the concentrations that they've predicted seem to exceed the safe limits that we've calculated. The vertical dashed line depicts that threshold. So above 1 is above the safe limit, below 1 is below the safe limit. And as you can see very clearly, ethinylestradiol, the sex hormone, and the carbamazepine, the anti-epileptic drug, they are mostly close to 100%, 100% of it is above the safe threshold in terms of water volume of the entire catchment. And to a certain degree, you also see that for diclofenac, maybe at, let's say, around 25% of the water volume also exceeds the safe limits. Now I'll jump into the human health risk assessment. Here we also had 2 questions. So these were, do these pharmaceuticals pose a concerning risk for human health, and which parameters seem to influence these risks? Again, if you keep track of this very simple formula for the risk, you need exposure concentrations and safe limits. For the safe limits, we went into the literature, scanning as many sources as we could to collect safe limits for the pharmaceuticals that we looked at, 12 in this case. And we've designed a model, an exposure model that accounted for different parameters and different factors. I'm not going to delve in too much detail about the model, but I will emphasize just a few things that I think are important to keep in mind in the exposure model that we've designed. So in terms of exposure for humans, we've considered 2 pathways. So 2 exposure pathways, the via oral and dermal. Inhalation was not included because for these type of chemicals, it can be neglected because they don't easily go into the gas phase. So then you should just be informed that we've divided the population into age groups. So different pharmaceutical uptakes and different risks for the pharmaceuticals for different age groups. We have infants, toddlers, children, adolescents, and adults. And also we've created, or we conceived what we call behavioral archetypes. And these are essentially behavioral profiles. So we've called the average archetype an individual that just assumes the average behavior in terms of consumption of fish and swimming activity, drinking water. And then, for example, you have the fisherman, which would be the exact same as the average, except for the fact that the fisherman archetype would be the type of individual that would consume fish way above the average person. And for the swimmer would be the same as the average, except for the fact that it swims at a way higher frequency and duration than other people, and so on. The extreme archetype simply assumes all the previous archetypes' behaviors. Furthermore, we've considered 5 exposure scenarios. So the diagram that you've seen before, right here. So this diagram was basically cloned 5 times for 5 different exposure scenarios, which simply mean that we've considered different environmental conditions for surface water concentrations and drinking water concentrations. The 5th one is distinct from all the other 4 because in this 5th we wanted to account not just for differences in behavior in adults, but we've also took into account what you could call abnormal behavior or excessive behavior in childhood as well. So we had all this data to plug into our model, and we've calculated around 7,500 uptake values for these pharmaceuticals. And once we've merged them so that it corresponds to a lifetime of exposure, and we combine all the exposure routes, the oral and dermal, we ended up with 375 risk quotients. And these can be summed up in this figure. It's a little bit blurry, but you don't need to zoom in too much. So the overall message here, or the main takeaways is that there doesn't seem to exist any exceedance of risk, at least overall throughout the catchment. There are a few, very few instances where the risk is indeed exceeded. Apparently, it is exceeded. Mostly downstream, immediately downstream of wastewater treatment plants or emission points. But still, there are very few minority. And also that happens mostly for the most extreme scenarios. So you have the scenario 4A and scenario 4B. So these are the most extreme scenarios, and still the risks do not often exceed the safe limit, as you see from the color label here. Also, in terms of archetypes, you can clearly see that the fisherman seems to be the type of individual that would be most at risk if environmental conditions were to be changed, as the extreme profile, extreme archetype. Doxycycline, from all the pharmaceuticals we analyzed, was the one that showed the highest percentage of exceedance of the safe limits. Phenazone, on the other hand, was the one that showed the lowest. Here I just wrote game changer for drinking water, just to emphasize that luckily for us, we live in countries where drinking water is very safe in terms of human health, at least as far as we could tell in this analysis. But if we were to be in a situation where drinking water was not sufficiently treated, or in other regions of the world where unfortunately they don't have access to water treatment technology as we do, then the drinking water can very easily overshadow certain environmental conditions. Next, yeah, so this is just a more detailed view into the distinction between the uptake for different age groups, as you see here on the left side. And then each column, big column, would be the exposure route. So we have the uptake via the skin when swimming, uptake via accidental swallowing of water while swimming, via the consumption of fish, and by the consumption of the drinking water. And from this figure, I would just emphasize, and the main takeaways would be that the uptake is pharmaceutical and archetype dependent, and they are very, very low. But still, the highest in relative terms was the diclofenac via fish consumption. So perhaps we could keep an eye on diclofenac, but given the safe limit associated with it, it's still not. It doesn't seem to be of concern from what we can tell from our assessment. Then finally, antimicrobial resistance risk. I don't know how much time I have left. Maybe 2 minutes or so.
A bit more than 2 minutes, indeed.
Okay, all right. So also, again, 2 questions for this module. So we asked ourselves if antibiotic selective pressure correlates with antibiotic resistant gene abundance, and does the environmental matrix also influence the antibiotic resistant gene abundance? So antibiotic selective pressure just relates to the fact that antibiotics can exert a selective pressure towards bacteria that possess genes that confer them resistance to those same antibiotics. And environmental matrices are simply, I'll show in the next slide actually. So it's just surface water, sediments, and wastewater. So those were the 3 matrices that we've considered in our modeling. And also we wanted to look at the antibiotics that had been measured in those same samples, and the abundance of resistant genes. So those three things combined. There are a lot of studies that do quantify quantify the concentration of antibiotics in, let's say, surface water. Many that do the same for resistant genes in surface water, but not necessarily all the three of them combined. Actually, just a bare few of them in the scientific literature. So we took all of that information. So essentially, we ended up with 25 studies from different countries, sampling years, antibiotic classes, and we've modeled it. So we corrected for those differences in the data to come up with a final output, which translated into in a very simplified graph that I simplified here. You can see on the lower axis the antibiotic selective pressure, so the ability for the mixture of antibiotics that exists in the sample, in the environmental sample, to exert a selective pressure towards certain resistant genes. And on the vertical axis, you see the abundance of resistant gene copies. And you can see that there seems to be a positive correlation between the two of them in terms of the surface water samples and the sediments. And the opposite seems to happen in wastewater, which was a little bit surprising to us. We were not quite expecting that. Of course, there might be something that we overlooked in our exercises, as it can always happen. But and is still work in development. But we don't quite know exactly why this is. We have some ideas and some hypotheses, but that can be discussed later. Just to emphasize the difference that you can see between the sediments and the surface water. So although with increasing amounts of antibiotics that you find in a sample, you could expect to a certain degree an increase also in the amount of the resistant genes in that sample. That seems to be more pronounced in sediment samples than in surface water, which also goes in line with some arguments that have been put forward in the last couple of years. But I won't go into that. I guess that's it. I hope I managed in time. Thank you so much for your attention.